Welcome. Welcome to the special class for entrance level preparation for all over India for JEE Mains, Advanced, NEET and other exams that happens in India. This is half a dozen. That means we will try to improve your concept so that you can actually do well in these kind of examinations. So today our topic for half a dozen is Gauss's theorem in electrostatics that we already have done in our class 12. So let us start with problems. A very interesting one. Let's do it. So I was telling you, we'll start with a very interesting problem for this half a dozen related to Gauss's theorem. Now let us read the problem first. They have given us that statement that let rho r is a function which is illustrated as q by pi capital R to the power 4 into r. So rho r is equal to capital Q divided by pi R to the power 4 small r. Be the charge density of a solid sphere. We are talking about a solid sphere, okay, of radius capital R. Total charge is capital Q. So we can see this expression. We can understand why they have given us like this. So this is a charge density, and obviously this is a sphere, so this is a volume charge density, because rho means volume charge density, lambda means linear, sigma means surface, and rho means volume charge density. Anyways, so we have to calculate the electric field at a point P which is at a distance r1 from the center. So it is outside or inside, that they have not mentioned. They have just mentioned that we have to find out the electric field at a distance r1 from the center. And this problem actually came in JEE Mains 2009. It was IEEE that time. But this is a very interesting and conceptual problem based on Gauss's theorem. Alright, so I have already written this. Actually, my main job is to find out what is the differential charge that can be present, because we have to take an elementary section of the sphere so that we can calculate the total amount of charge and electric field over there, and then we can integrate for the whole thing. This is the general aspect for most of the sums, where they give you a general scenario and they ask us to find out a particular expression for a given point. So we have this approach of taking the elementary section of the sphere. So we have the sphere which is capital R, the radius is given here. We have taken an elementary strip within the sphere, or within the spherical shell. We have taken a small shell which is at a distance small r, and the depth or the width of that shell is dr. So we want to know what is the charge which is present on this particular shell that we have imagined at a distance small r, and the width of the shell is dr. So obviously dq is the charge density we have. So obviously we can say that dq is equal to rho r, that is the charge density, into volume, obviously volume of this section. So you can write clearly capital Q by pi R to the power 4. Now it is at a distance r, so r whatever is given here, and the volume of the spherical shell is definitely what? We can find out the spherical surface area, which is 4 pi r square, and we can easily multiply with the width so that we can get the volume of the spherical shell that we have calculated. So this is the amount of dq. Very good. So next what we have to do is we have to find out the total charge, and that is the integration of dq, but with the proper limit. So we have to take something out, obviously. So what I am getting is q by pi r to the power 4 into 4 pi, that we can take out common, and we have this variable which is r cube dr. This is what, but we have a limit. Now what is the limit? From the center till this distance, you can see r1. So 0 to r1 will be our limit. So if I integrate, obviously the total charge that we can say, this is the total charge I am telling you. So if you integrate, what I am going to get? This will give you, obviously you can understand, it is q by r to the power 4. 4 is here again, this pi will get cancelled. So let us be 4q by r to the power 4, and here it is r1 to the power 4 divided by 4. If you integrate and put the limit, you will get this answer definitely. So what is the final expression of the charge? It is q into r to the power 4 divided by capital R to the power 4. I'm sorry, this will be R1. Anyways, so this is the expression we have derived. This is the total charge. Now what we have to do, we have to calculate the electric field. Okay, and according to Gauss's theorem, we have already understood this thing, that electric field for a charged sphere is 1 by 4 pi epsilon naught total charge by the distance square. This we already know. Outside the sphere or inside, whatever it is a general expression. So obviously now we can assume that this is the total charge in a solid sphere which is concentrated, as the magnitude is this, and then we can find out the electric field. See the process, okay? See the process. First we have calculated the total charge and we have somehow used the Gauss's theorem, because we have taken the elementary section and we calculated the total charge in order to find out. In Gauss's theorem it was mentioned that it is 1 by epsilon naught times of the total charge being enclosed. So here also we have enclosed the total charge. We have found out what is the total charge that we can enclose, and you can find out the electric field at that particular point. See, this is the interesting concept that you have to understand. Now the rest of the part is just two lines that you can easily solve, and that is, if you come to calculate the value of E, it is definitely is equal to 1 by 4 pi epsilon naught, and it is total charge by the distance square, which you can, this q you can replace this, say this is q dash, let us take this is q dash, because there is one q already inside, so we get confused. So this is the total charge, so q dash, or the total charge by r1 square. So you can put the value of this obviously. So what I'm getting finally, you can easily understand, it is 1 by 4 pi epsilon naught, or let us write here, it is 1 by 4 pi epsilon naught, and then you can see here it is capital Q small r1 square by capital R to the power 4. So this is the correct answer for the electric field. This is the way we can solve this. And what concepts we have learned from this that we are going to use for other stuff that will come in entrance, because it may own come. It has already came at JEE Mains at 2009. It's an old problem, but the concept here is to identify the total amount of charge, because Gauss's theorem always get this stress that it is 1 by epsilon naught times of the total charge enclosed. And since here we are talking about the electric field to calculate, so obviously we can use directly this form which was derived by Gauss's theorem. This expression we derived from Gauss's theorem, so we are using it directly, and we are not writing 1 by epsilon naught times of the total charge. That also we can do, but we will be doing the same process of finding out the electric field for a charged spherical solid. So that we are not using. This is entrance. We have to do it fast, and you can understand this is the way we can solve this problem. Okay. Now we'll go to the next one.
This is our second problem of this half a dozen, and this is the most interesting and conceptual problem of today's class. What it says is that a disk of radius a by 4 having uniformly distributed charge of 6 coulomb is placed in the xy plane with its center at minus a comma 2 comma 0 comma 0. This coordinate is very important and very tricky as well. A rod of length a, small a, carrying a uniformly distributed charge of 8 coulomb is placed on the x-axis from x equals to a by 4 to x equals to 5a by 4. This is also given in the diagram, you can see that. And there are 2 point charges of minus 7c coulomb and 3 coulomb, which are placed at a comma 4 comma minus a comma 4 comma 0 and minus 3a comma 4 3a comma by 4 comma 0 respectively. So consider a cubical surface formed by 6 surfaces, which is given as x equals to plus minus a by 2, y equals to plus minus a by 2, and z equals to plus minus a by 2. The electric flux through this cubical surface we have to calculate. So you have understood there are a lot of 3D geometry here, and you have to visualize a lot of things. So let's start.
So now the problem is clear to you, and this is a very interesting sum to understand Gauss's theorem properly. Okay, just only the statement of Gauss's theorem is enough to do this sum. Alright. So you see, they have given us a lot of charges. They have given us one charge which is 3c, which is placed in a particular coordinate they have given. We have a minus 7c charge which is within the coordinate of a by 2. Okay, because you see they have given us a cube which is have the position, the vertices you see in the sum, it is given plus minus a by 2, comma plus minus a by 2, comma plus minus a by 2. So we have a cube where every these points, I have drawn only a square, I mean kind of, draw a square. This looks almost like a rectangle, but doesn't matter. So all these points, they are having a coordinates of a by 2, comma a by 2 for this 2D, and if we go for 3D, then z is also a by 2, plus or minus. Okay, so that is very interesting. And also they have given us a rod having a total charge of plus 8c, which is placed from a point a by 4 to some 5 a by 4 this way. And there is also a disk which is having a center which is minus a by 2, comma 0, comma 0, which is this point, because this is the outline of the cube where we are enclosing all these charges. Now the important fact here is that in this diagram, what we can understand, please try to understand that Gauss's theorem states that it is the total electric flux is equal to 1 by epsilon naught times of the total charge enclosed. Very good. So this is we are going to use here. So flux is basically 1 by epsilon naught times of summation q. So now we have to identify which are the charges and how much charges are being enclosed by this cube that we are imagining, with the vertices plus minus a by 2, comma plus minus a by 2, comma plus minus a by 2. Alright, so I hope you can imagine this, right? Sure? Great. So now we are going to write 1 by epsilon naught times of the total charge. Now charge, what are the objects that are carrying charges? This one, this one, this one, and this one. Alright. Now what I can see that the location, what are the coordinates given by this plus 3c charge is not lying within the cube. So this charge is not considered anymore. Alright. We have another minus 7c charge that we can include because this is within the domain of the cube. So we can write minus 7c, great, plus what else we have? We have this much portion is basically 1/4 of the rod. So if it is 1/4, then obviously 1/4 of the total charge will be enclosed, which is sorry, don't write C here. Total, okay. And what else? The next thing is this disk, which is having this center. So this much portion is outside. So this is half of the disk, right? So we can write half into the total charge of the disk, which is 6 coulomb, and this is the total. This is the total charge of the summation Q is. So obviously you can understand what will be the electric flux. You can just simply calculate minus 7 plus 2 plus 3. Alright, minus 7 plus 2 and then plus 3, which is what is? Which is nothing but is equal to minus 2 coulomb. 2 coulomb. So 2 by epsilon naught will be the correct answer for this kind of question, to find out the total electric flux enclosed by this cube having coordinates a by 2 plus minus comma plus minus a by 2 comma plus minus a by 2. Isn't it interesting? You see, only the statement is required to do this sum, and it came in IIT 2009. You can understand how questions are asked, so please develop the concept. Don't ignore any simple, even a single line of the chapter, so that you can have these concepts to do these sums. Alright, now we'll move to another interesting one coming now.
Here is a new problem. It's an integer type problem which came in. You can see that IIT 2009, that means JEE Advanced now 2009. And it says that a solid sphere of radius capital R has a charge capital Q distributed in its volume with a charge density rho is a volume charge density rho equals to k into r to the power small r to the power small a, where k is a constant, a is a constant, and small r is the distance from its center. Okay, so this expression that rho equals to k r to the power small a, this particular expression is definitely suggesting us that we have to form certain elementary section and then we have to integrate, because this function will help us there. Anyways, let us continue with the sum. It's now telling us that if the electric field at small r equals to capital R by 2 is 1 by 8 times that of small r equals to capital R, that means at the surface of this particular sphere, solid sphere, find the value of small a. We have to calculate this, and the answer should come within should be an integer ranging from 0 to 9. This is the common process of integer type questions that comes in JEE Advanced. So let's start. I hope you have understood the problem and you have written this in your class book. Okay, let's start.
So in a nutshell, we know what is the problem. This is the integer type question that comes in JEE Advanced, and it is also from 2009. But this one is again a very interesting one. This will develop a lot of concepts. See what they have given. That they have given one relation. That relation is the electric field at R by 2 in 1 by 8 times of the electric field at R. So let us calculate what is the electric field according to the Gauss's theorem, the concept for the charged spherical shell and all. We know electric field is 1 by 4 pi epsilon naught total charge by R square. That is what electric field means in Gauss's theorem, because we have a charge distribution. We do not have a single charge, alright, or 3-4 charges where we can apply superposition theorem. You have to identify when you have to use Gauss's theorem. When you have a charge distribution, it is evident that you have to use Gauss's theorem. Alright, so let's see how we can calculate this ER, that is electric field at the radius at the point which is equal to from the center, the distance is capital R, and the sphere is also having a radius of capital R. That's what they have mentioned. So it is definitely summation q by r square. Just now we did a problem where we did calculated the total charge enclosed, because in Gauss's theorem it is very important to identify how much charge we can enclose. Alright, so fine enough. So they have given us a volume charge density which is rho equals to k r to the power a, which is to find out. We have to calculate this value. Alright, anyways, and this is the information given. This is the info given, and that is what that is also an information, but this value we don't know. We have to calculate this value using this relation. Alright, so we have somehow summarized the problem and what we have to do. Okay, sure. So now ER, what I can write 1 by 4 pi epsilon naught, and then dq is obviously is rho dv, right? What will be the limit from 0 to capital R, and this capital R square will remain as it is because this is there already. Now what is rho? So let us write integration. This is 4 pi epsilon naught r square. Great. And what is rho? Is k into r to the power a. And what is dv? What is dv? Okay. In the beginning, what sum we did, from that concept we know that dv can be calculated by this way, which is 4 pi r square into dr. That is the volume of that spherical shell we can take, so that we can apply the limit. Okay, remember just now we did one sum from and we are using that concept here. Alright? Okay, so this is all about great enough. So we have to take out certain things. We can see that k into 4 pi, this will get outside, and k 4 pi by 4 pi epsilon naught capital R square integration r to the power a plus 2 and dr. Okay, so easily you can understand what is going to come. This 4 pi will get cancelled. K by epsilon naught capital R square into, this is what, r to the power a plus 2. So 1 by a plus 3 is evident to come. The power comes down, and this is capital R to the power a plus 3, because integration 1 power will add it up. Anyways, so r square this. So finally the expression is k by epsilon naught into a plus 3 into, you can see if I divide a plus 3 and r square here, we can easily understand this is going to come r to the power a plus 1. So this is the electric field at a distance which is equal to E electric field at a distance capital R from the center. So similarly, let us calculate about R by 2. Now what I can do, we have this expression already where we have integrated and find out the solution. So easily we can understand that this expression will lead us to the same thing, but there will be one additional part, and that is this will now become r by 2 to the power a plus 1. So this is what we are fetching from this calculation. We are not redoing the calculation. Can you follow me? Because we have shortage of time. Anyways, so this is all about and they have given that er by 2, that means this one, er by 2 is 1 by 8 times of er. Okay, I think you can understand now that the problem is almost solved because we do not have much more to do here. Clear? Great. So this is what we have, and we have to calculate the value of A. So a lot of things are getting cancelled, right? And we are getting r to the power a plus 1 into half to the power a plus 1 is equal to 1 by 8 into r to the power a plus 1. You can understand, I mean expanding, these all will get cancelled, nothing will remain. Okay, so this is also getting cancelled. Alright, so what is remaining? I'm sorry, half to the power a plus 1 is equal to 1 by 8, which is half to the power 3. So now it is a sum of plus 8 because you can understand. So the integral value of a is 2. So this is the solution of this problem. You see, initially this problem was something so heavy, but when we applied the concept one by one, it came to be very simple. You see, my aim in this half a dozen is to develop the concepts within you so that you can easily, assess the sum and easily can approach to the sum. And I don't think after solving this problem you are finding, okay, this was a huge one. It wasn't. Okay, only we had few calculations which are very, very, very simple, provided we had the concept properly. Alright, now let's check a very important concept that will come up with a picture now.
This is a very different type of problem. The problems we did till now, this is completely from a different domain, but it involves Gauss's theorem in a different way. Okay, so what it says that a uniformly charged thin spherical shell of radius capital R carries a uniform surface charge density sigma per unit area. It is made of two hemispherical shells, and here is the trick: held together by pressing them with force capital F as seen in the figure, and we have to find what F is proportional to what. Okay, so we have few data like the radius capital R, surface charge density sigma, and the spherical shell is made of hemispherical shells which are kept together by pressing them with the force capital F. Okay, so let's see. It came in IIT 2010, that means almost 10 years back. Anyways, but this is a very conceptual and very interesting problem. Let's see how we can solve it.
So you have understood the problem, and here is a very interesting fact about Gauss's theorem. This sum is very much different. Okay, why it is different? Because they are saying that we are pressing two hemispheres to form a sphere, and that force they have asked us to find. So now you can understand that this force you are exerting on the hemisphere, when you are pushing it, you are actually applying a pressure. So what is pressure? Is thrust per area. Great. Now what is the pressure in electrostatics for this kind of cases? You can remember this as a general expression, you can use it later on. I am just showing you how to calculate the pressure. It's very simple. Force is Q into E by A, and Q by A is sigma, and again the electric field, considering this surface, this is kind of imaginary surface where both ways the charges are present. So we can write that this is equal to epsilon naught by sigma by 2 epsilon naught. So finally pressure is sigma square by 2 epsilon naught. Now what do we have to find? We have to find the force by which we can make these two hemispherical spheres to get attached in spite of they are having similar charges or similar charge density. So they will repel each other, we are forcing it, we are pressing it, we are giving pressure in order to make them united. Great. So what is force then? Force is definitely is pressure into area, and this surface is definitely is pi capital R square. So you can easily understand that the final expression is this one, which is the force. So why we can say the force is proportional to, you can understand pi, 2, these are all constant, dimensionless constants, so we can remove this and we can write this is proportional to sigma square capital R square by epsilon naught. This is our answer for this kind of question. So you can understood the one thing, where we are applying the concept of Gauss's theorem here, but we are not directly applying the concept of Gauss's theorem. We are applying, but we are applying in a different method, because they have asked us to find out the force which will help the spheres or the hemispheres to get united like a single sphere. So we have a concept of pressure because we are pushing it. Alright, so this is what is very important, and please understand this concept. This came in entrance exam in 2010 or 11. I don't exactly remember the year, but it came, and this concept is very much different from the sums you usually encounter, and that's why it will develop a particular concept base within you, which will help us to to go further and solve greater problems, better problems, other problems in the actual entrance that we are going to face in 2021. Alright, now we are going to for the next one, which is another interesting problem which will come up now.
Seems very easy. It is actually, but it also have a lot of small concepts that we usually ignore while we study Gauss's theorem. So here let us see that how these small things are also very important. Linear charge having linear charge density lambda penetrates a cube diagonally, and then it penetrates a sphere diametrically as shown. So one is diagonally and another is diametrically, and we have to find what is the ratio of flux coming cut of the cube and sphere, of course. So just jot down this information that whatever we have linear charge distribution and we have linear charge density, so length is important, and we have one arrangement diagonally, another arrangement diametrically of a sphere and of a cube. So let's start. This is more geometric, but this is very interesting too. Write it down in your classwork.
So I hope that you have already written down the next problem that we are going to do, and you have already understood we have a cube, we have a circle or a sphere, and what we have seen that within this cube or sphere we have charged rod which is lying there. That means, and even they have also mentioned about the linear charge density. Alright, so it is a linear distribution of charge, it is related to lambda, and for linear distribution of charge we have to find the ratio of flux for the cube and the sphere respectively. So in this way we have to understand the basic of Gauss's theorem, which states that total flux enclosed is 1 by epsilon naught times of the total charge enclosed by the surface. Alright, so let us first think about the cube. What is the diagonal of a cube? The diagonal is where A is the side of the cube, it is A by root 3. This you know already in lower classes. In mensuration you did this in class 7-8. Alright, but why I have taken the diagonal? Because you see the rod which is lying, or the charges which are lying on the rod is actually the diagonal of the cube. Alright, so what is the flux here? Flux here is the total charge by epsilon naught, and the total charge is lambda into dl, where dl is the length of the diagonal. So what I can get, it is lambda A by epsilon naught root 3. This is the flux one for the cube. Very good. And for the spherical section, what I can say, it is lying along the diameter. Okay, so again it is lambda dl by epsilon naught. And what is dl? dl is the length of the diameter of the sphere or circle, whatever they have given. So dl is equal to 2a, which is the diameter, okay, of the sphere, and then it is epsilon naught. So this is the thing. Now you can, I'm sorry, this is for the second one, ratio. So now you can take the ratio phi1 by phi2. Then what you can say, the lambda will get cancelled, epsilon will also get cancelled. And what is the final answer then? It is obviously 2 is to root 3. That is the final answer here. You can understand, this is equal to 2 is to root 3. Phi1 by phi2, you can say, is 2 is to root 3. Alright, so this is the, or root 3 by 2. If you do phi2 by phi1, it will be root 3 by 2. Anyways, the more or less the thing is like this. Alright, great. Now we'll go to the concluding part of this half a dozen, the sixth one. That means the half dozen sums we have already covered, and also there was a concept which will come up after this section. Anyways, so this is another very interesting sum based on Gauss's theorem. What they have said, I am not writing the problem, but I am telling you, please write it down. They have said that a sphere of radius small a, the sphere of radius small a is having a total charge of plus 3q, and it is enclosed by a spherical shell of radius small b, and they have mentioned that b is greater than a. This is mentioned. Okay, so there is a sphere which is having a plus 3q charge of radius small a. There is a spherical shell which is enclosing the sphere with a charge of minus q here, minus q, and it's having a radius small b which is greater than a. Alright, they have asked us to find out the electric field at a point which is at a distance capital R from the center, and they have also mentioned this capital R is less than b but it is greater than a. This they have mentioned. So we have to calculate the electric field. Alright, so we'll go back to the concepts of Gauss's theorem. We'll identify that what is the situation here. There can be induction. I told you in the normal board class, I told you a problem where we thought about this induced charge. But here, when we think about this, let us think that we have to calculate the electric field for this dotted boundary, alright? And the sphere of radius small a is carrying a charge of plus 3q is within this boundary, alright? So inside this boundary, the electric field is 0. So electric field is 0 till this point, that is for sure, because the Gaussian surface, the imaginary surface which is enclosing the charge, how much charge it is enclosing? It is enclosing only plus 3q. It is not enclosing minus q. Okay, so the induction effect of plus 3q on minus q, or induction effect of minus 3q on plus 3q is not valid, because we are given a boundary which is in between. So it is only enclosing the charge which is residing on the sphere of radius small a. Is that concept clear? Why we are not enclosing the surface which is having a radius of small b and carrying a minus q charge? Because it is outside of our reference point, and the charges which we cannot enclose according to Gauss's theorem or by a Gaussian surface, we cannot have any calculation related to that. Whenever it is outside the Gaussian surface, that is not our consideration. This is very important, because this type of problem usually comes in entrance, and people, I have seen my lot of students have done this mistake, that they consider everything. But we need not to consider everything. We have to consider only thing which is being enclosed by the Gaussian surface or the imaginary surface that we call. Alright, so how much charge we are enclosing? Plus 3q. What is the electric field? We need not to do anything, we have solved the problem. what is the electric field? It is 1 by 4 pi epsilon naught total charge by distance square, because it is lying outside the sphere. Within the sphere, electric field till the boundary is there will be a value. Within the sphere, there will be no value. And since we are taking only this surface, we are not taking this minus q charge. Even we are not taking the induction effect on plus 3q. Okay, so this is what we have. So this is the expression: electric field is equal to 1 by 4 pi epsilon naught 3q by r square, and this is the final answer. Alright, so I hope you have understood along this the process of knowing the 6 different type of problems, that in Gauss's theorem, how much charge we are enclosing, what is the total amount of charge we are enclosing, and how we can apply the concept of electric field for different Gaussian surfaces that we have already done in your board syllabus. That is very important. Like in this sum, we calculated everything with related to linear charge density. So lambda dl was the total charge. But here again we visualized that what is the total amount of charge we are enclosing by a Gaussian surface. This is the fun, this is the fun, to identify what is the amount of charge we are enclosing. The rest amount of charge is not our consideration. We can easily remove this, and this is how we approach to solving the problems related to Gauss's theorem. And this kind of problem usually comes in entrance. I hope these concepts will definitely give you the confidence to face those problems which are going to come in entrance in 2021. Alright, now I'll just give you a simple concept or a concept base that I didn't give in the board classes, and this is half a dozen. So I'm showing you another picture which will conclude this lesson. Alright, so please see, and please then sit with your textbook, and I'll be sending you assignments so that you will be confident about how to solve problems in entrance related to electrostatics or Gauss's theorem or other chapters. Alright, till then, bye bye.
Okay, so this is to wind up today's class, and you can see that there are electric fields. The calculation of electric fields for different types of charge distributions are shown here in this particular diagram. Please copy this diagram in your classwork and try to understand why these expressions are coming. Try to calculate these expressions, and these informations are very important while you are thinking about to crack the All India entrance examinations. Okay, so I'm winding up today's class. Okay, I'll expect that you'll sit with your textbook and other assignments that I'll send in our Accenters WhatsApp group, and complete those and try to gather as much as concepts you can. Okay, and we'll be doing our next lesson very soon. Till then, bye bye, stay safe and stay productive. Okay.